What is a geostationary satellite and mention its uses? If the period of revolution of an artificial satellite is equal to the period of rotation of Earth, then such a satellite is called geostationary satellite. The time period of a geostationary satellite is 24 hours. Coming to the uses of a geostationary satellite, a geostationary satellite is used to study the upper layers of the atmosphere. They are used to forecast the changes in atmosphere. They are used to know the shape and size of the earth. Geostationary satellites are used to identify the minerals and natural resources present inside and on the surface of the earth. Also, the geostationary satellites transmit the TV programs to distant objects. Geostationary satellites undertake space research, that is, to know about the planets, satellites, comets, etc. If two places are at the same height from the mean sea level, one is a mountain and other is in air, at which place will the value of G be greater? State the reason for your answer. So this is the next question in the series. From the relation between small g and capital G, we can write small g is equal to Gm by r square, where small g will be representing acceleration due to gravity, capital G the gravitational constant, m mass, and r the distance. But we know from the definition of density, rho is equal to m by v, mass by volume. From this, mass becomes the product of volume and density. The earth is said to be spherical in shape. Volume should be taken as 4 by 3 pi r cube, the volume of the sphere, multiplied by the density representing rho. When you substitute the value of m in the formula G is equal to Gm by r square, we get G is equal to G by r square into 4 by 3 pi r cube rho. Here r square and r square get cancelled, so r will be left over. So finally G is equal to 4 by 3 pi r G rho. From this it is clear that acceleration due to gravity and density are directly proportional. So the density is more at mountains. The weight of an object is more at the poles than at the equator. At which of these can we get more sugar for the same weight? State the reason for your answer. The answer comes out like this. We know weight is given by the product of mass and gravity. W is equal to mg. So the weight of the object at poles is equal to mass at the poles multiplied by acceleration due to gravity at poles. Similarly, the weight of the object at equator is equal to mass at the equator into acceleration due to gravity at the equator. Given weight of the object at poles is greater than the weight of the object at equator, because the acceleration due to gravity at equator is less than at poles. Hence, we can get more sugar at equator. If a nut becomes loose and gets detached from a satellite revolving around the earth, will it fall down to earth or will it revolve around earth? Give reasons for your answer. The answer for this is, when a nut is detached from a satellite revolving around the earth, the nut is also moving with the speed of the satellite, as the orbit of the satellite does not depend upon its mass. Hence, nut is moving in the same orbit under centripetal force. An object projected with a velocity greater than or equal to 11.2 kilometers will not return to the earth. Explain the reason. The answer: the escape velocity on the surface of the earth VE is equal to 11.2 km per second. Any object projected with the velocity greater than or equal to 11.2 kilometers per second will not come back because it has overcome the Earth's gravitational pull. The following are the very short answers from the chapter Gravitation, and these questions are completely based on the textbook. Here we start with the first question. State the unit and dimension of the universal gravitation constant. From Newton's universal gravitational law, the force of attraction between any two bodies in this universe is given by F is equal to G m1 m2 by d square, where G is universal gravitational constant. Its units are Newton meter square per kg square. Now moving on to the dimensional formula of gravitational constant. From the formula F is equal to G m1 m2 by d square, we can write G is equal to F into d square by m1 m2. Here F refers force, which has a dimensional formula m1 L1 T minus 2. m1 and m2 are the masses whose dimensional formula will be m1 and m1. D square represents the distance given by L2. Simplifying these, we get m minus 1 L3 T minus 2. Now let us move on to the next question. State the vector form of Newton's law of gravitation. The answer is, the vector form of Newton's law of gravitation is F is equal to minus G m1 m2 by r cube into r, where r cap is the unit vector. The next question. If the gravitational force of Earth on the Moon is F, what is the gravitational force of Moon on Earth? Do these forces form an action-reaction pair? The answer is, the gravitational forces on the Earth and on the Moon, they form an action and reaction pair. What would be the change in acceleration due to gravity at the surface if the radius of Earth decreases by 2%, keeping the mass of the Earth constant? The answer is, this is a numerical given in very short answer questions. From the relation between small g and capital G, we have G is equal to Gm by r square, which proves that acceleration due to gravity small g and radius r are inversely related. Thus we can write G1 by G2 is equal to r2 square by r1 square, or you can reverse G and r on either sides and write as G2 by G1 is equal to r1 square by r2 square. Since the radius of Earth is said to be decreased by 2%, we can write R2 as 98 by 100 R1. This is because the radius of Earth has been decreased by 2%. Suppose it is decreased by 4%, then R2 will be 96 by 100 into R1. Now let us try to substitute all these data in the formula. G2 by G1 is equal to R1 square by 98 by 100 into R1 square. R1 and R1 get cancelled. The remaining is G2 by G1 is equal to 100 into 100 by 98 into 98. On simplification, we get this as 1.04. Thus, G2 by G1 is equal to 1.04. This can also be written as G2 by G1 minus 1 is equal to 1.04 minus 1. Taking LCM this side, we get G2 by G1 by G1 is equal to 0.04. Let us continue with the next question in this series. As we go from one planet to another, how will the mass and the weight of a body change? The answer is the mass of a body. Mass is a scalar quantity, hence it does not change with the direction or the place. Hence, mass remains constant at any place. Weight is given by the product of mass and gravity. That means weight depends on acceleration due to gravity, and we know the acceleration due to gravity changes from place to place. Thus, the component or the physical quantity called weight that depends on acceleration due to gravity also changes. Thus, we can conclude the mass remains constant and the weight changes from one planet to another planet. Keeping the length of the simple pendulum constant, will the time period be the same on all planets? Support your answer with the reason. The answer is no. Time period depends on acceleration due to gravity. Time period is given by the formula T is equal to 2 pi root L by G. From this formula we can observe that G value varies from planet to planet, so time period also changes. Thus we can conclude that the time period and gravity are interrelated. Give the equation for the value of G at a depth d from the surface of Earth. What is the value of G at the center of Earth? The answer is the value of acceleration due to gravity at a depth d represented by Gd is given by G into 1 minus d by r, where d is the depth and r is the radius of the Earth. At the center of the Earth, the value of acceleration due to gravity is 0. What are the factors that make G the least at the equator and maximum at the poles? The answer is the value of acceleration due to gravity G is maximum at poles due to rotation of Earth. Earth is flattened at the poles. The equatorial radius is less at the poles. The value of acceleration due to gravity G will be minimum at equator due to rotation of the Earth and bulging near the equator. Hydrogen is in abundance around the Sun but not around Earth. Explain. The answer is the escape velocity on the Sun is 620 km per second and that on the Earth is 11.2 km per second. The RMS velocities of hydrogen, which is 2 km per second, is less than escape velocity on the Sun. So, hydrogen is more abundant around the Sun and less around the Earth. What is the time period of revolution of a geostationary satellite? Does it rotate from west to east or from east to west? Time period of a geostationary satellite is 24 hours. It rotates from west to east. A geostationary satellite is one whose period of rotation is equal to the rotation of Earth. Thus it is 24 hours. What are polar satellites? The answer is polar satellites are low altitude satellites which are rotating at a distance of 500 to 800 km. They go round the poles of the Earth in a north-south direction. Its time period is around 100 minutes. Let us move on to the numericals given in academy textbook. The first one is two spherical balls each of mass 1 kg are placed 1 centimeter apart. Find the gravitational force of attraction between them. This is the numerical. The solution. If you just observe, it is given that the two spherical balls has equal masses. So we can consider that m1 is equal to m2 is equal to 1 kg. Let us write the given data first. The distance between the balls is 1 centimeter. When we change this into SI system, we get 1 into 10 power minus 2 meters. The value of gravitational constant capital G is equal to 6.67 into 10 power minus 11 Newton meter square per kg square. The force of attraction between two bodies is given from Newton's universal gravitational law as F is equal to G m1 m2 by d square. Substituting the given values, we get F is equal to 6.67 into 10 power minus 11 into 1 by 1 into 10 power minus 2 whole square. On simplification, we get 6.67 into 10 power minus 7 Newton. The mass of a ball is 4 times the mass of another ball. When these balls are separated by a distance 10 centimeter, the force of gravitation between them is 6.67 into 10 power minus 7 Newton. Find the masses of the two balls. The solution. So this is the given numerical. First, let us write the data given in the numerical. It is given that the force between the two balls F is equal to 6.67 into 10 power minus 7 Newton. And of course, we know the value of gravitational constant capital G as 6.67 into 10 power minus 11 Newton meter square per kg square. The distance between the balls D is given as 10 centimeter. Taking this into meters, we get 10 into 10 power minus 2 meter. The important concept in this numerical is the mass of the second body is 4 times the mass of the first body. So, let us assume the mass of the first body m1 as m. So, m2 becomes 4m. Substituting all these in Newton's universal gravitational law, F is equal to G m1 m2 by d square, we get 6.67 into 10 power minus 7 is equal to 6.67 into 10 power minus 11 into m into 4m by 10 into 10 power minus 2 whole square. On simplification, we get 4m square is equal to 10 power 2. Otherwise, m square is equal to 100 by 4, which is equal to 25, and we know m is nothing but the value of m1. So therefore, the mass of the first body m1 is equal to 5 kg and the mass of second body m2 is equal to 4m, which is equal to 4 into 5, that is 20 kg. The third numerical in this series. 3 spherical balls of masses 1 kg, 2 kg and 3 kg are placed at the corners of an equilateral triangle of side 1 meter. Find the magnitude of gravitational force exerted by the 2 kg and 3 kg masses. The solution. The force of attraction at 2 kg on the 1 kg particle is assumed to be F2 and it is given by G m by d square, which is equal to G into 1 into 2 by 1 square. F2 is equal to 2g. Similarly, the force between 3 kg and 1 kg mass denoted by F3 is given by G m by d square again, which comes out to G into 3 into 1 by 1 square, which is 3g. So, the force between 3 kg and 1 kg, which is represented as F3, is 3g. Now, let us find out the resultant force. The resultant force is given by F is equal to square root of F2 square plus F3 square plus 2 F2 F3 cos theta. As F2 is 2g and F3 is 3g, we can write as square root of 4g square plus 9g square plus 2 into 2g into 3g into cos 60. Cos 60 is equal to 1 by 2. So on simplification, we get square root of 4g square plus 9g square plus 6g square, which is equal to root 19g. Moving on to the next numerical in this series. At a certain height above the Earth's surface, the acceleration due to gravity is 4% to its value at the surface of the Earth. Determine the height. The solution. Let the acceleration due to gravity at a height denoted by gh is equal to 4% of acceleration due to gravity on Earth. GH is equal to 4 by 100 into G, and the radius of the earth is taken as 6400 kilometer. Substituting these in, GH is equal to G by 1 plus h by r whole square, which is the formula to calculate acceleration due to gravity at a height h. We get 4g by 100 is equal to g by 1 plus h by r whole square. As we need to find out h, let us separate 1 plus h by r whole square, which is equal to 100 by 4, after cancelling g and g on either sides. Now 1 plus h by r whole square is equal to 25, or 1 plus h by r is equal to square root of 25, which is 5. Now h by r is equal to 5 minus 1 equal to 4. Thus height h is equal to 4 times the radius r. So the final answer will be 4 into 6400 kilometer, which comes out to 25,600 kilometer. A satellite is orbiting the earth at a height of 1000 kilometer. Find its orbital speed. The solution: the height at which the orbit is placed is 1000 kilometer. The radius of the earth, as we know, is taken as 6400 kilometer. Value of capital G is 6.67 into 10 power minus 11 Newton meter square per kg square, and mass of the earth is 6 into 10 power 24 kg. Substituting all these in the formula for orbital velocity, VO is equal to root gm by r plus h, we get V naught is equal to square root of 6.67 into 10 power minus 11 into 6 into 10 power 24 by 7400 kilometers, which is the sum of radius of the earth 6400 plus the height at which the satellite is mentioned in the problem as 1000. So 6400 plus 1000 becomes 7400 kilometers, also can be written as 7400 into 10 power 3. On simplification, we get V naught as square root of 0.5408 into 10 power 10, which is 73.54 into 10 power 3 meter per second, otherwise 7.354 kilometer per second. A satellite orbits the earth at a height equal to the radius of the earth. Find its orbital speed and period of revolution. The solution: first, let us notify the given data. It is given that the satellite is at a height equal to the radius of the earth, hence height h is equal to r. We know the value of capital G is 6.67 into 10 power minus 11 Newton meter square per kg square, and the mass of the earth is 6 into 10 power 24 kg. Also, the radius of the earth is 6400 kilometer. Substituting all this data in the formula of orbital speed, V naught is equal to root of gm by r plus h. V naught is equal to root of gm by r plus r, since height h is equal to the radius of the earth in this problem, which is equal to root of gm by 2r. Substituting the values, V naught is equal to root of 6.67 into 10 power minus 11 into 6 into 10 power 24 by 2 into 6400 into 10 power 3. On simplification, we get V naught is equal to square root of 0.3126 into 10 power 8, which is equal to 0.5592 into 10 power 4, otherwise 5592 meter per second. Writing this in kilometers, we can write it as V naught is equal to 5.592 kilometer per second. Time period T is equal to 2 pi r plus h by V naught. that is equal to 2 pi into 2r by v naught, since h is equal to r here again, that is equal to 4 into 3.14 into 2 into 6400 into 10 power 3 by 5.592 into 10 power 3. On simplification, we get 14,374.8 second. Otherwise, we can write it as 1.44 into 10 power 4 second. Converting this into hours, we get T is equal to 4 hours. The gravitational force of attraction between two objects decreases by 36% when the distance between them is increased by 4 meters. Find the original distance between them. The solution: from the information given in the numerical, let us prepare the data required for solving this problem. Let the initial force is F. It is given that the gravitational force is decreasing by 36%. So F2 becomes 64 by 100 F. Similarly, let the distance between the two bodies is d1, which is taken as d. As the distance has been increased by 4 meters, let us take d2 is equal to d plus 4 meters. We know that force and distance are inversely proportional from Newton's universal gravitational law. So we can write F1 by F2 is equal to d2 square by d1 square. F 64 F by 100 d plus 4 by d whole square. Here this F and F get cancelled. 100 goes to the numerator. Thus on LHS it becomes 100 by 64. Moving on to the other side. When you simplify this d plus 4 by d whole square, let us take square root on both sides. So on LHS it becomes 10 by 8, and on the RHS the square and root get cancelled. It will be d plus 4 by d. 10 by 8. Let us cancel this with 2. We get 5 by 4. So 5 by 4 is equal to d plus 4 by d. Otherwise we can write 5d is equal to 4d plus 16. D is equal to 16 meters. 4 identical masses of M are kept at the corners of a square of side A. Find the gravitational force exerted on one of the masses by the other masses. The solution: let us consider a square like this. These are the 4 sides of the square. It is given that masses of equal magnitude are placed at the 4 corners of the square. So let us calculate the force between the first and the second body, given by F of 1 2 is equal to gm square by a square. The base for this formula is Newton's universal gravitational law, which is F is equal to g m1 m2 by r square. Here g is gravitational constant. Masses m1 m2 will be the masses at positions 1 and 2. As they are equal masses, they become m into m, which becomes m square. The distance, we had considered the square of side A. So the distance between bodies 1 and 2 will be a, hence we had taken as a square here. Of course, following Newton's universal gravitational law. Simultaneously, let us calculate the force between 1 and 3. The distance between 1 and 3 becomes root 2a. This can be easily explained once you consider Pythagoras theorem here. The distance between 1 and 2 is a, and the distance between 2 and 3 is also a, as it is a uniform square. Now, knowing these two adjacent sides, the magnitude of the diagonal is calculated from Pythagoras theorem as AC is equal to square root of AC square plus BC square. So from this, the distance between the bodies 1 and 3 becomes root 2a. Now, knowing this distance, let us calculate the force. Force F of 1 3 is equal to g m square by root 2a whole square, which becomes 2a square. Similarly, let us calculate the force between bodies 3 and 4. It will be as similar as the force between 1 and 2. So the force between first and fourth body F of 1 4 is equal to gm square by a square again. Let us calculate the magnitude of all the forces. F is equal to square root of f of 1 2 square plus f of 1 4 square plus f of 1 3. This is equal to square root of gm square by a square whole square plus gm square by a square whole square plus gm square by a square, which is equal to gm square by a square into root 2 plus gm square by 2a square. On simplification, this becomes f is equal to gm square by a square into root 2 plus 1 by 2. Two spherical balls of 1 kg and 4 kg are separated by a distance of 12 centimeter. Find the distance of the point from the 1 kg mass at which the gravitational force on any mass becomes 0. The solution: mass of the first body m1 is equal to 1 kg, mass of the second body m2 is equal to 4 kg. The distance between the bodies r is equal to 12 centimeter. The distance at which the resultant magnetic intensity, the distance at which the resultant gravitational force becomes 0 is given by x is equal to r by root of m2 by m1 plus 1. So x is equal to, the distance is 12 centimeter. So let us take 12 by root of 4 by 1 plus 1. So this becomes 12 by root 4 is 2, 2 by 1 is 2, 2 plus 1. This can be further written as 12 by 3. 12 by 3 is nothing but 4. So at a distance of 4 centimeter, the resultant gravitational force is 0. Three uniform spheres, each of mass m and radius r, are kept in such a way that each touches the other two. Find the magnitude of the gravitational force on any one of the spheres due to the other two. The solution: if you just go through the numerical, we can understand that there are three uniform spheres which are kept in such a way that every sphere touches every other two spheres. So we can arrange these three spheres in the form of a triangle like this. Now, at the corners of this triangle, let us assume that there are masses of m, n at each corner, and this triangle resembles an equilateral triangle, and we know in an equilateral triangle the angle is 60 degree. To find out the resultant force, we can use the formula F is equal to square root of F1 square plus F2 square plus 2 F1 F2 cos theta. Here the masses and the distances are same, hence the force also will be same. So we can write F1 is equal to F2. Substituting this in the above formula, we get F is equal to square root of F1 square plus F1 square plus 2 F1 plus 2 F1 cos 60 degree. We know cos 60 degree is root 3 by 2. The 2 and 2 get cancelled. So the remaining component is F is equal to F1 square plus F1 square plus F1 under root 3. So the remaining is F is equal to root 3 F1. But we know from Newton's universal gravitational law, the force between any two bodies can be calculated from the formula F is equal to G m1 m2 by r square. So here, since the masses are equal, m1 and m2, m1 into m2 becomes m square, and the distance here is 2r because the radius of each uniform sphere is considered as r. So this distance becomes 2r. The distance between the two bodies becomes 2r. So we can write F1 is equal to g m square by 2r whole square. Otherwise, F is equal to root 3 g m square by 4r square. Two satellites are revolving around the Earth at different heights. The ratio of their orbital speeds is 2:1. If one of them is at a height of 100 km, What is the height of other satellite? The solution. In the numerical, it is given that two satellites are revolving around the Earth. So, the satellites are said to possess orbital velocity, and it is given that the orbital speeds are in the ratio 2:1. VO of 1 by VO of 2 is equal to 2 by 1. Let us assume it as height of the first satellite H1. So, H1 is equal to 100 km. Now, we have orbital velocity VO is equal to root of gm by r. When height is given, the formula becomes VO is equal to root gm by r plus h. From this, we can infer that orbital velocity and distance. Here in this numerical, the distance is r plus h. So, the orbital velocity and the distance r plus h are inversely related. So, the formula for this particular numerical comes out as VO of 1 by VO of 2 is equal to r plus h2 under square root by r plus h1 under square root. We had assumed VO of 1 by VO of 2 is equal to 2 by 1. So, let us substitute that. So, 2 by 1 is equal to square root of r plus h2 by r plus 100. To remove this square root, let us square on the other side. So, this 2 by 1 becomes 4 by 1 is equal to r plus h2 by r plus 100. On cross multiplication, we get 4r plus 400 is equal to r plus h2. Otherwise, h2 is equal to 3r plus 400, that is equal to 3 into 6400, r being the radius of the earth, we had taken it as 6400 here, plus 400, that is equal to 19200 plus 400, which comes out to 19600 kilometer. So, the second satellite is at a height 19600 kilometer. A satellite is revolving round in a circular orbit with a speed of 8 km per second at a height where the value of acceleration due to gravity is 8 meter per second square. How high is the satellite from the Earth's surface? You are asked to take the radius of the planet as 6000 km instead of the actual radius 6400 km. The solution. Now first let us write the data given in the problem. Orbital velocity V0 is equal to 8 km per second, also can be taken as 8000 meter per second. Acceleration due to gravity at a certain height gh is equal to 8 meter per second square, and radius capital R is equal to 6000 kilometer, otherwise 6000 into 10 power 3 meter. Now orbital velocity at a given height V0 is given by root of gm by r plus h is equal to square root of g into r plus h. Otherwise VO square is equal to g into r plus h. Substituting the given data, 8000 square is equal to 8 into 6000 into 10 power 3 plus h. 6000 into 10 power 3 plus h is equal to 8 into 10 power 6. We had squared 8000 here. From this, h is equal to 8 minus 6 into 10 power 6. 8 minus 6 is 2. So, h is equal to 2 into 10 power 6 meter, otherwise 2000 kilometer. Calculate the escape velocity of a body from the Earth's surface. Also, if the Earth were made of wood, its mass would be 10% of its current mass. What would be the escape velocity if the Earth were made up of wood? The solution. The radius of the Earth is 6400 kilometer, otherwise 6400 into 10 power 3 meter. The escape velocity V is given by root of 2gr, which comes out as root 2 into 9.8 into 6400 into 10 power 3. On simplification, we get this as 11.2 kilometer per second. Now moving on to the second bit in the same problem. The escape velocity when Earth is supposed to be made up of wood is taken as VEW here, and the escape velocity of ordinary earth is taken as VEE in this numerical. Also, the mass of the earth when it is supposed to be made up of wood is taken as MW, and mass of the ordinary earth is taken as ME. When earth is assumed to be made up of wood, its mass MW will be 10% that of ME. Since escape velocity and mass are directly proportional, we can use the formula VEW by VEE is equal to square root of MW by ME. Substituting the values, VEW by VEE is equal to square root of 10 of ME by 100 ME, because MW is taken as 10% of ME, 10% in the sense 10 by 100. Finding the square root of here after cancelling ME and ME, we get 1 by root 10. So, VEW is equal to 1 by root 10 of VEE, which is 11.2 the actual escape velocity, by root 10 is taken as 3.162. Thus, the escape velocity when earth is supposed to be made up of wood, VEW, comes out as 3.536 km per second. This was vivid information on the concept. Hope you have followed. If you have any sort of difficulty in understanding the concept, just freeze the video at the place where you did not follow. Go through the content again and again till you get it. Don't hesitate. If you still feel it difficulty to understand, please don't hesitate at all either to call me on the number 63098243665 or mail me at kvrphysics369@gmail.com. Once I receive the message on WhatsApp on this number or in the email, I'll respond personally to your query and help you out in solving your problem. Thank you for watching. See you again in the next video. Bye-bye.